Hey everyone, and welcome. Today, we're going to tackle one of the most important and honestly, one of the weirdest concepts in all of data science. It's called the curse of dimensionality. And believe me, it's this bizarre phenomenon that completely breaks our intuition and can secretly totally sabotage our machine learning models. I mean, think about it. We're all taught that more data is always better, right? If you want a more accurate model, you add more features, more columns, more information. It seems so obvious. But what if I told you that's not always true? That after a certain point, adding more data can actually make your model dramatically worse. So this whole paradox, it was actually first spotted way back in the 1960s by a mathematician named Richard Bellman. And as he was working with more and more features, he started to see this dark side to all that data. He discovered something strange was happening, and he's the one who gave it its very cool, kind of spooky name, the Curse of Dimensionality. Okay, so let's really break this down. What does that name even mean? Well, formally, the curse describes what happens when the number of features, the dimensions, in your data starts to grow. The space that your data lives in, it just expands exponentially. It grows so fast that your data points get spread thinner and thinner until they're like a few lonely stars in a vast, ever-expanding universe. Now, to really wrap our heads around this curse, we have to take a little journey. Seriously. We're going to a place where all the normal rules of geometry, the stuff you learned in school, they just completely fall apart. We're taking a trip into high-dimensional space. All right, let's start with something familiar, something we can actually picture. Imagine a circle drawn perfectly inside a square, okay? That circle takes up a pretty big chunk of the area, right? Over 78%. Now let's pop into 3D, a sphere inside a cube. It still takes up over half the volume, 52%. This all feels normal, intuitive. The thing in the middle is taking up most of the space. But this is where things get really, really weird. Look what happens when we keep adding dimensions. By the time we get to just 10 dimensions, that hypersphere in the middle, it only takes up 1/4% of the volume. And at 100 dimensions, its volume is, it's basically zero. It's gone. The center of the space has become completely, utterly empty. So that leads to a really bizarre question, doesn't it? If the center is empty, where did all the volume go? Well, it rushed out to the corners. And this is the first mind-bending rule of high dimensions you have to accept. All of your data points are effectively living at the extreme edges of the space. There is no middle anymore. And just when you think it can't get any stranger, it does. This quote perfectly captures the second bizarre phenomenon. Just think about this for a second. In high dimensions, the distance to your nearest neighbor is almost the same as the distance to your farthest neighbor. I mean, let that sink in. The whole idea of a neighborhood just breaks down. Your closest data point is basically just as far away as your most distant one. The word near just loses all meaning. Okay, so we've got these super weird geometric properties. Empty centers, neighbors that aren't really neighbors. Why should we care? I mean, who cares about hyperspheres, right? Well, we should care because these exact properties are what cause many of our most trusted machine learning algorithms to get completely and totally lost. I mean, take an algorithm like k-nearest neighbors. Its whole job relies on finding the closest points to make a prediction. But if every point is basically equally far away, how can it find the nearest ones? It can't. The algorithm is just guessing. And clustering? It fails for the exact same reason. And worse, because the space is so vast and empty, it becomes incredibly easy for your model to find meaningless patterns in the noise and just completely overfit. And this isn't just theory, okay? It's a real, well-documented effect. It's called the Hughes phenomenon. And it's this idea that as you add more and more features, your model's accuracy might go up for a little bit, but then it hits a peak and it starts to fall. You heard that right. Adding more information can literally make your model perform worse. Okay, so this sounds pretty bad. We're trapped in this high-dimensional wilderness. Everything is far apart. Our algorithms are broken. So how do we get out? How do we escape? Well, thankfully, data scientists have figured out two main strategies, two paths to guide us out of this mess. All right, the first path is called dimensionality reduction. And the analogy here is just perfect. Think of it like creating a shadow puppet. You take your really complex high-dimensional data and you project it into a lower dimensional shadow that still captures its most essential shape.
Then there's the second strategy, feature selection. This one is more like packing for a trip. You look at every single feature you have, and you only pack the essentials, the ones that are actually useful, and you leave all the junk behind. So, a classic example of dimensionality reduction is an algorithm called PCA, or Principal Component Analysis. Now, instead of just picking and choosing features, PCA is much smarter. It looks at your data and it finds the direction where everything is most spread out, where the most action is happening. Then it creates a brand new axis, a new feature that summarizes all that action. It's a really clever way of combining your old, weaker features into a few new, super potent ones. And for that second strategy, feature selection, you got a few flavors to choose from. First, you have filter methods. These are kind of the quick and dirty approach. They just rank features using simple stats tests before you even start modeling. Then you have wrapper methods. These are way more powerful, but also slower because they actually use your model to test out different combinations of features to see what works best. And finally, you have embedded methods, which are probably the most elegant. They build feature selection right into the model's training process. Super efficient. All right, that was a deep dive into a very, very strange world. So let's pull it all back together. Let's create a clear map of the key things you absolutely have to remember next time you find yourself navigating high-dimensional data. So here's your map. First, and most importantly, high-dimensional space is just plain weird. Your intuition will fail you. Volume vanishes and distances get all warped. Second, remember this is the curse that breaks machine learning algorithms, especially any that rely on the idea of nearness. Third, your escape plan has two main paths: dimensionality reduction, where you create new, powerful features, or feature selection, where you pick only the best original ones. And finally, and this is crucial, whichever path you choose, always use cross-validation to make sure you're not just fooling yourself. You've got to make sure you're finding real patterns, not just chasing high-dimensional ghosts. And that really brings us to the end. Look, this isn't just some abstract theory, right? It's a very real, practical challenge that affects pretty much anyone working with complex data sets today. So I'm going to leave you with this one question to think about. There's a good chance this curse is hiding in your data right now. So how are you going to be the one to break the spell?